The problem session. Today in this problem we have this is also from JEE 2025 and this is from paper 2. Okay, back to the problem. This is question 8 and it's a thermo problem, thermodynamics. For physics students is a lot of scary subject here but not that much to know. So you have to know about Carnot engine. Carnot engine operates between two temperatures. You have a TH, T cold, and TH. So this is some reservoir. This is temperature. So this represents like a big, TH represents like a big container filled with material at temperature TH. And this represents another big container TC. And you have some some material that will go through this. So this TH, and it will operate between this, and then go back. So at TH, it's going to absorb so whatever this is the system. You put in here, it's going to absorb some heat QH and it's going to expand, etc. And this will TC, when I bring this guy into this, the heat will absorb by the reservoir. And difference of these two, difference of this QH minus QC is the work. And Carnot is ideal, so all of this goes into work. Okay, so in Carnot, in this case you have also the ratio of these two is equal to the ratio of the temperatures, temperature in absolute scale. This is how absolute scale actually defined, and also called Kelvin. So this is true in Carnot. So another thing you got to know is in the Carnot, efficiency of any engine, efficiency of all engines is how much work you got and how much heat you put in. Which is the same as 1 minus QC over QH. This for all engine. But the Carnot has this one more property. So Carnot, in addition to this W over QH and 1 minus QC over QH, because of Carnot, 1 minus TC over TH. So this is what you have to know for the engines to do this problem. So just a review of Carnot Engine here. So they give you some TH. So they give TH. They give it a Carnot. And they also give QH per cycle. The work extracted from this engine, so whatever the work, so between this and this you can get out the work. So we used to run a heat pump. Now a heat pump works in the opposite way to like Carnot. And instead of efficiency, it has a coefficient performance. So let's look at heat pump. What the heat pump? In the heat pump, you are going to do some work, and there will be some energy obtained from the lower temperature, and then energy in one cycle will go. So this will be the energy flow. So instead of that, let's start the primes so that we don't get confused with the same symbols used everywhere. Coefficient of performance, which is also sometimes written as letter beta symbol, is, you see here, this is the cost. Here, this is the cost. This is going to be flip over. So this is the output we want, and that's the cost. So it's going to define like that. So you can see from just this will come back to its original state after all of this flow of energy. So this plus this has to be that. So QH prime will and then you can do the same trick as you do above. It's going to be 1 over 1 minus QC prime over QH prime. Now, if this is ideal, which it doesn't say in the problem, but assumes that you can assume this is going to be 1 over 1 minus TC prime over TH prime will be equal to 1 over TH prime over TH prime minus TC prime. You can see if you were to do this guy, it will be TH minus TC over TC. So it's just inverse of those. All right, so that's it. And what's given here is just here, but it says that W prime here is that W produced over there. So if you look at the diagram, you have a TH, TC, some TH, TC prime, some TH prime. So it's going to produce some W. W will flow, QH prime will go, QC prime, and QH was like this, and QC. So this is like a energy cycle. This is for the heat pump, Carnot cycle, pump, Carnot engine. Let's call it Carnot engine. So this W is same as W prime. All right, now let's look at the math here. So it says work extracted from Carnot Engine is this. Oh, this is very simple, right? We have a W over QH is it, and from there this 0.4, and this is 150, and this is that is just 60. So this is correct. Now this one says cold reservoir. Now so this will be eta C 1 minus Tc over Th, and so this is 0.4. So this means Tc equals 0.6 Th, and Th is 1000, so that makes 600. That's also correct. Now for the heat pump, so we used 60 joules for the heat pump. So we used beta equals to 10, W prime equals to W is 60 joules, and it's asking for Tc prime. Something went wrong with my pen. So right over there. So we have 1 over 1 minus Tc prime, Th prime. From this, it is beta. So just try a little bit of algebra before put anything. 1 over beta, 1 minus Tc prime over Th prime. So bring Tc prime over Th prime equals to 1 minus 1 over beta, beta minus 1 over beta. So Tc prime is beta minus 1 over beta Th prime. So 10 minus 1, 10. And for heat reservoir, hot reservoir for the heat pump is 300. So that's 300. 9 over 30. So that looks like that's correct. Heat supplied to the hot reservoir, the heat pump. So this time it's asking for QH prime, and this is getting a little annoying. So what's the QH prime? I worked out all this over here. We can use just this guy. So QH prime should be just equal to beta W prime. The same as beta W is 10 times 60 is 600 joules. Okay, let's see what they have. It says 540 joules, which is incorrect. So these are 3 correct answers. All right, that was that was a kind of little bit review and solving the problem. So if I didn't have to review it, probably I can do it in 2 minutes. So this is pretty straightforward Carnot engine heat pump problem, and you should be ready for this kind of problem in the test. All right, so I'll see you in the next video. Bye.